Greetings to one and all present here. My name is Anish Advani, and today I will be talking about advanced forms of GPS. I'll be starting this presentation by defining what navigation is. Then I'll be talking about satellite navigation systems, followed by which I'll be giving a brief introduction to Global Positioning Systems, GPS. I'll be talking about its working, the advanced forms that are currently being used in the modern world, and legalities involved with its usage. At the end of this presentation, I'll be concluding it with a short conclusion. Navigation. Navigation is the determination of position, direction, and velocity of a moving vehicle. The translation motion of a vehicle is described by a six-component state vector that comprises of three position components and three velocity components. This process of measuring and calculating the state vector on board the vehicle can also be stated as navigation. Satellite navigation systems. Apart from the other navigation systems that are currently being used in the modern world, satellite navigation systems fulfill requirement for an accurate global navigation assistance. At present, there are two fully functional global navigation satellite systems, GNSS. These are the Global Positioning System, GPS, operated by the United States of America, the Global Navigation Satellite System, GLONASS, operated by the Russian Federation. These two GNSS were initially used for military purposes, but now are open to civil use. Galileo, which is operated by European Space Agency, is a GNSS which is under development. GPS comprises of three system segments. These system segments are a space segment, a control segment, and a user segment. I'll be talking about the space segment first. The space segment comprises of the satellite constellation. The original GPS constellation, also known as the notional constellation, had 24 satellites, but at present there are 31 operational satellites in the current constellation. The GPS constellation consists of six circular orbital planes, which are at a height of 20,200 kilometers, which is almost twice the diameter of Earth, as can be seen in the figure towards your right, and they are at an angle of 55 degrees to the equator. These orbital planes can accommodate about 4 to 6 satellites, and at any position and time, about 5 to 8 satellites will always be in line of sight of a receiver. Although the orbital planes increase up to 55-degree north and south, the coverage is global because of their height. The orbital period of these satellites is 11 hours and 58 minutes. Therefore, the satellites orbit Earth around twice each day. The next segment is the control segment. The purpose of a control segment is not just to upload the data, but also to monitor the satellite's health and to control their operation. This segment consists of three major elements. The first one is the monitor station, which aids in tracking the transmitted signal from satellites and collecting measurements. The second is master control station, which uses the measurements collected by the monitor station to predict the FMSs and the time history of the satellite, and to upload the parameters modulated by the satellites onto the transmitted signal. The third one is the ground antenna, which uploads navigation data and sends commands to the signal for general control. The next segment is the user segment, which comprises of a receiving equipment, which includes antennas and receivers, and a set of processors that performs the navigation solution to provide the user with positioning, velocity, and precise time. Working of GPS. The GPS relays signals on three frequency bands. These frequency bands are L1, which operates at a frequency of 1575.42 MHz, L2, which operates at a frequency of 1227.60 MHz, and L5, which operates at a frequency of 1176.45 MHz. The GPS alpha band is one of the new signals and is part of the GPS modernization plan. It broadcasts on a radio signal band reserved specifically just for aviation safety services. The satellites have an onboard atomic clock which provides precise time T1 at which the radio signals are broadcasted with their positioning. The GPS device receives and notes the exact time of arrival T2 of the radio signals. It then uses arrival time of the radio signals to calculate its distance from each satellite in view. The distance between the satellite and a GPS device can be given by the product of speed of light with which the signals travel through space and the travel time it takes to reach to the user. The travel time of a signal is equal to the difference between the time at which the signal was broadcasted by the satellite T1 and the time at which the signal was received by the GPS device T2. On determination, on determining its distance from at least 4 satellites, a GPS device can use geometry to establish its 3D location on Earth. Advanced forms of GPS. The first one that I would like to talk about is the airborne-based augmentation system, which is used to rectify the system error quicker and to notify the user about the malfunction in the system as soon as possible. There are 3 methods to do this. The first one is to increase the number of satellites in view by using GPS with another satellite system. This method helps the effect of propagation error as it uses 2 separate frequencies. The second one is RAIM, which stands for Receiver Autonomous Integrity Monitoring System, which monitors data integrated by using an extra satellite. Receivers usually use 4 satellites for a 3D fix and 3 satellites for a 2D fix. When RAIM is monitoring the navigation solution, a 3D fix requires 5 satellites, whereas a 2D fix requires 4. The third method is using Aircraft Autonomous Integrity Monitoring, AAIM system, which integrates satellite positioning with alternative conventional navigation systems to improve accuracy and reliability. The next is ground-based augmentation system, which computes ground measurements of the signal errors and relays them to several users to enable correction to the raw GPS data. The several methods that can be used for this are differential GPS, which is DGPS. The differential GPS is a form of a GBAS and improves system accuracy by 1 to 3 meters. The ground installation receives GPS signals by a continuous receiver at an accurately surveyed location, computing the difference between its known location and the one received from the GPS. It then sends the correction to any aircraft within a range of 30 kilometers using an aircraft communication addressing and reporting system ACARS data link. The next method is by using pseudolights or pseudo satellites. Pseudolights or pseudo satellites is a development of DGPS, which includes an extra ground station that acts like another satellite. It gives another range input, hence increases the accuracy of the fix, especially in the vertical plane. The next system I would like to talk about is satellite-based augmentation systems. Since DGPS and pseudolights provide a high-level accuracy only on a small range, SBAS applies the same basic principle over a wide area. An example of SBAS is Wide Area Augmentation System, WAAS, which is a development in the United States of America. Just like GPS, SBAS comprises of a ground segment, a space segment, and a user segment consisting of airborne SBAS receivers. The ground segment comprises of several wide area reference stations, WARS, that continuously download satellite data and pass the information via data links to the wide area master station, WAMS. The data collected by the WAMS is used to determine the differential correction for each satellite that is being tracked. After the data is collected and organized, it is broadcasted to the ground Earth station, which is then uplinked to the space segment. The space segment uses a geostationary satellite system that allows transmission of the message over a wide area to all users modulated on the GPS L1 frequency. Next, I would like to talk about the legality. Conventional navigation systems like Very High Frequency Omnidirectional Range VOR and distance measuring equipment's DME receivers must be installed on board the aircraft as a backup if GPS fails. A standalone GPS must either be integrated with systems like automatic DME/DME fixing or RAIM facility. When GPS is the only equipment being used, which meets basic radio navigation (BRNAV) standards, The RAM availability must be confirmed before the airplane takes off. If it is predicted that RAM will not be available for more than 5 minutes, the flight does not go through. During flight, if an aircraft is using a standalone GPS for meeting DRNAV standards, conventional navigation aids must be always used as a backup in case GPS fails. In case of IAM failure on a standalone GPS aircraft can continue using the GPS. Position data must be cross-checked with traditional navigation aids. If there is a position error between the two datasets, GPS position should be disregarded, and the conventional navigation system should be used for the flight. I would like to conclude by saying that satellite navigation systems are the most reliable and widely used navigation services in the modern world. GPS provides with an accurate navigational aid in the aviation sector and otherwise. The recent development in GPS has made satellite navigation more accurate and reliable. Thank you.